I'm Jack Erickson, Product Marketing for FPGA, ASIC, and SoC Development, and I'm here with Dr. Georgia Zucchelli, Product Marketing for Analog Mixed Signal Development, and we will show you how to generate SystemVerilog DPI models from Simulink for use in your AMS simulations. One of the biggest challenges with mixed signal design is verifying the digital logic and analog circuitry working together. Simulation tools are optimized for digital or for analog, so it's often easier for engineers to just focus on the domain that they specialize in, relying on the specification to guide their functionality. The two sides are integrated late in the design cycle after each has been designed and implemented, and this is often where problems are found because one side had to make functional changes or the specification was vague or incomplete. And at this stage, the designs contain so much implementation detail that simulation is slow and debug is really difficult. Analog and digital simulation environments both offer ways to import models of the other side, but creating these models adds overhead to each design team, and often the actual design changes due to requirements changes or bug fixes, and the models are not updated. The ideal methodology is to model and simulate analog and digital functional behavior at a high level using solvers and data types native to these domains, like you can in Simulink. And a lot of innovative projects do this. But too often the next step is to capture this behavior in specification documents to pass to the design teams, leaving them to work in isolation on implementing their respective subsystems. A truly connected top-down approach will continuously refine each domain with implementation detail, automate the transformation to lower-level implementation, and continuously integrate the domains. One way to get started toward this vision is to start generating verification models from each domain for use in designing the other. Analog and digital simulators both support the SystemVerilog Direct Programming Interface, or DPI, for modeling external components, golden references, stimulus, or anything else you need to verify your design. You can use HDL Verifier to automatically generate these models as C code with DPI wrappers from Simulink or from MATLAB. It works for any model or MATLAB code that supports C code generation and allows you to model synchronous fixed-point digital logic or continuous time real number analog circuitry. For a demonstration of how this works, I will turn it over to Georgia to demonstrate how to generate SystemVerilog DPI components from Simulink for use in Cadence AMS Designer.
What I'm going to demonstrate now is how to generate SystemVerilog components from a Simulink model. And I will use a Simulink model that embeds continuous time and discrete time signals. That is to say, a Simulink model that embeds behavioral description of the analog and the digital subsystems. What are the steps to generate the SystemVerilog components? Well, essentially it consists of generating C code, ANSI standard C code, and together with the C code generate automatically a SystemVerilog wrapper that uses the Direct Programming Interface, DPI-C, to import the C code and invoke the C code in an AC design tool. So after generating the C code and the SystemVerilog wrapper, we will import these components into Cadence Virtuoso AMS Designer and perform a discrete time simulation that is equivalent to the Simulink simulation. The workflow consists of 3 steps: generate the C code, generate the wrapper, and import the wrapper, and this provides functionally equivalent description in Simulink and in Cadence AMS Designer. Without further ado, let's actually jump into the demo and see how this workflow actually works in practice. To cover this topic, I'm going to use an example based on a simple but representative sigma delta analog to digital converter. The converter is composed by 4 stages: a source, a low-pass filter, a first-order sigma delta, and a decimator filter. I'm going to generate SystemVerilog components for each of the stages. So we will have 4 SystemVerilog components at the end, and we will import them in AMS Designer. So what we will obtain is 4 functional stages that are equivalent to Simulink and that provide exactly the same results in Simulink and in AMS Designer. The 4 stages of the model are respectively a signal source, that in this case is just a sine wave, sinusoidal waveform, an analog low-pass filter that is just designed with a behavioral Butterworth third-order function, a first-order sigma delta that takes a continuous time signal indicated in black and generates a fixed rate, fixed time step signal indicated in red. Please notice the light gray block is a block that computes when the signal crosses zero and generates a sample when such an event occurs. The last stage is a decimator. The output of the sigma delta is highly sampled and affected by noise at the high frequency that is removed by this low-pass decimator filter. This is a multi-stage, multi-rate decimation filter designed with DSP system toolbox. So you see the output of the sigma delta has a lot of noise in the higher frequency. The output of the decimator is filtered out and is also reduced in sample rate. Please notice that all the signals in this test bench are or double floating point data type. This example represents a behavioral description of a multi-rate system. That is to say, a system where blocks are executed with different rates, involving continuous time signals indicated in black and discrete rate signals indicated with colors. The following demonstration will show how to export this model from Simulink and import it in AMS Designer, so to create this view. What are the necessary steps required to achieve this result? First of all, you need to make sure that the Simulink model is ready for generating C code. Then you need to generate the C code and the SystemVerilog wrapper for importing the C code. You need to compile the C code and create a shared object that will be dynamically linked to our mixed signal simulation. You need to import the SystemVerilog modules and build a test bench for the simulation in AMS Designer. And finally create a scheduling for the simulation of the system. So let's start with the first step. We need to make sure that the Simulink model is ready for generating C code. What does it mean in practice? Essentially, it means that we need to use a fixed step solver rather than a variable step solver. This is really the critical point of the entire translation. In fact, in many mixed signal systems, such as in this one, it is often convenient to use a variable step solver to simulate the system, because this allows to achieve faster simulation results and acute accuracy. However, variable step solvers are not supported for C code generation. The reason is straightforward. The generated C code doesn't have a sense of time and therefore doesn't deploy the simulation solver. For this reason, we need to use a fixed step solver. We can change the solver by simply going to the model configuration parameters and decide if to use a fixed step or a variable step solver. However, when we change the solver from variable step to fixed step, simulation results might change. So for this reason, it's important to verify that the results are correct. For this reason, I'm going to log the results using the ability to log critical output, such as the output of the sigma delta and of the decimator. When I now run the simulation, the Simulink Data Inspector will allow me to inspect the results and compare successive run of the simulation. This simulation has been run with a variable step solver, and we will see now in a second the results that we can achieve. We can see now that the Simulator Data Inspector has captured the output of the sigma delta, that is essentially a bipolar signal that toggles between -1 and 1, as well as the output of the decimator filter, that is our sine wave as it is been reconstructed. Notice the delay that is introduced by the filters in the system. We can now go back to our simulation settings, change the solver to use a fixed step solver. We can fix the time step to a certain amount. In this case, I've chosen 10 time step for the fastest rate in my signal, just as a qualitative measure, and I now can rerun the simulation. After rerunning the simulation, I can then compare the results of successive runs and assess if the fixed step solver with the given time step is providing sufficiently good results, correct results, or not. I can inspect the results visually by simply overlaying the traces, or I can compare the runs. And when comparing the runs, I can also specify the tolerances for evaluating absolute and relative, for evaluating the difference in between the signal. In this case, as you can see, using a fixed time step that is 10 times smaller than the max, just for the sake of demonstration, I can now go back to the system, use a much larger time step, rerun the simulation, and we can now verify that, of course, results will not be as positive and as conservative. Now you can see that actually the differences are much more relevant. You need to make sure that a fixed step solver is used. This is essentially the most critical step in the entire translation. Essentially, it is task of the user to assess when good is good enough and find the most suitable trade-off between simulation speed and accurate result. Now that I'm using a fixed step solver, I can now choose the target for generating C code. Again, from the configuration parameters, I can simply choose code generation and select the target for generating SystemVerilog components. Essentially, I'm generating C code that will be using the DPI-C, the direct programming interface of SystemVerilog, in order to import the C description of the models into SystemVerilog. For this particular example, I'm also using a custom template for the generation of the wrapper. The wrapper will be pin compatible with the Simulink subsystem and will not include additional clock or reset signals. This, of course, makes it more intuitive for analog and mixed signal example. After choosing the target and the template for the wrapper, I can generate C code for each of the 4 subsystems. So let's make, for example, generate the C code for the source. The C code is put in a folder where the user can find all the necessary C and header files to recompile the code. There is no dependency from the MathWorks library or from the MathWorks licenses. The C code can be recompiled on any platform that is provided with an ANSI C compiler. During the generation of the code, also a make file is provided, so to facilitate the compilation process. And the SystemVerilog wrapper, compliant with the template that we provided, is generated. The SystemVerilog wrapper, as you can see, is a SystemVerilog module that allows to invoke the C code function initialize, update, and output. If you look into more detail into this wrapper, we will actually see that it requires 2 events, the update and the output, to schedule when the C code is invoked. We will see that actually the C code consists of 3 functions, an initialize, an output, and update function. Why do we need 3 functions? Essentially to reproduce the simulation steps. Initialize is the function that should be invoked before the simulation starts to make sure that initial states and conditions are properly defined. The update function is the function that is used to update any possible internal state that you could have, for example, in filters. And the function output is the function that is invoked when we need to assign the output and compute the output of our function. So as you can see, the function initialize is also only invoked once, and the function update is invoked at every time that the DPI update event occurs. And the function output is invoked every time that the event DPI output occurs. This is a wrapper that has been generated with a custom template. You can customize this template as you prefer, so to make this wrapper friendly with the type of application that you have in mind. So this is just essentially an example of how we can invoke these functions. These events will have to be defined in the simulation setup in AMS Designer. In other words, we will have to tell AMS Designer when these events occur, and when these events occur will determine when the C code functions are executed. I can now generate C code for each of the subsystems. After repeating the operation for each of the blocks, I get as many folders, as many subsystems, in this case 4. So what I can do for my own convenience is simply copy all the C and header files into a general folder and then compile them all together into a single shared object. So as you can see, here I generated a shared object that contains all the compiled code, and it's called ADC underscore DPI underscore 64 because I compiled it with the 64-bit option .so. It's a shared object because I'm currently running Linux Red Hat 6. Now I'm ready to import the components in AMS Designer. From AMS Designer, I can simply define new cell view and simply import the SystemVerilog description that has been automatically generated. So let's say that we are going to generate a cell that is called source test. I can simply copy in here the SystemVerilog code wrapper that has been just generated in Simulink. I need to make sure that the name of the module is compliant with the name that I assigned in the library manager. As soon as the component is imported, then AMS Designer will automatically generate a symbol for it, and this symbol can be used in the test bench. I can now build a test bench by simply dragging and dropping all the components that I've just generated. So the source, the analog filter, the sigma delta, and the decimator. It is important also to associate a config view so to be able to perform a mixed signal simulation. This will also allow me to, for example, toggle some of this view instead of using a behavioral SystemVerilog view, using a circuit level implementation of the same system. The last bit of this demonstration that is currently missing is a scheduler block. That is to say, a block that specifies the invocation rate of each of the subsystems. The scheduler must be manually made by the user. The scheduler is required because nor the C code nor the SystemVerilog wrapper have any notion of time. Therefore, we need to tell the simulator where each of the blocks are invoked. If we look at the scheduler, essentially there are two clock signals that defines the rate of the faster and of the slower part of the system. We have a faster rate that defines the invocation rate of the source and the analog low-pass filter that will be equivalent to those 0.2 picoseconds that we have seen in Simulink. And then we have a slower rate that defines the invocation rate of the sigma delta and of the decimator. As you can see here, we have the two clocks, and each of the two clocks define when the events will occur that will schedule the invocation of the C code function as defined in the SystemVerilog wrapper. Once that we have a wrapper, we can now choose our AMS simulator, load a state or define a new state for the simulation, just perform a transient analysis, log the signals, and run the simulation. As you will see, the simulation is actually running very fast, with equivalent performances that we have seen in Simulink in AMS Designer. And of course, results are in agreement between AMS Designer and Simulink. Essentially, we are simulating exactly the same code with exactly the same rate. Before I conclude my demonstration, I would like to answer a frequently asked question. Often users ask me, can I still generate code if I use physical modeling components, such as Simscape components or Sim Electronics components? The answer is straightforward. Is yes, you can still generate C code and use the DPI C wrapper to import it in SystemVerilog and in AMS Designer. In this example that I'm opening here, you will see how I changed the analog low-pass filter using SIM electronics components. And I can use these components for the generation of the C code, just like I did for any of the existing subsystems. So what have we seen so far? We're saying we can generate C code from your Simulink model, including also analog continuous time signal. That we can automatically wrap the C code using the DPI-C interface and therefore invoke this C code in a SystemVerilog environment. And last but not least, we have seen how to import, build and simulate equivalent behavioral SystemVerilog models in your IC design tools, and namely Cadence Virtuoso AMS Designer. The advantages of this approach is that it's fast to simulate because it uses the native API of SystemVerilog, no co-simulation, single engine simulation. It is IC tool design independent. It is customizable, so you can change the template to comply with your requirements. And at the same time, it leverages a mature technology that is the C code generation from Simulink. It is mostly suitable for test bench generation and IC verification, where you need to script your design and sweep through many simulations and change parameters. And it supports, as I already mentioned, both discrete and continuous time signal. With this short demonstration, I end up the example on how to generate SystemVerilog components from analog mixed signal examples in Simulink and import them in Cadence Virtuoso AMS Designer. Thank you very much for your attention.
Designing analog and digital mixed signal functionality together at a high level and automatically generating models helps keep each domain up to date with the other side's progress so there are no surprises late in the schedule. This enables a true top-down design approach that can deliver significant benefits. What you saw here was just a small part of it. You can learn more from some of our actual customers by checking out their MATLAB Expo videos as shown here. The links are below. And you can click on Contact Sales to follow up and learn more directly from a MathWorks applications engineer.